Hello everyone, this is Dylan Bishop filming the project design of my actual hardware design that I've developed for our Capstone project. Here we have the actual project itself, this portion, and this here is going to be our master board, and this little board here will be our slave device. This all can be explained in the PowerPoint presentation that will be visible during our project presentations. This is just a demonstration of the actual hardware itself. So here we have our device, and over here we have a 12-volt battery out of a vehicle that this is where we're going to be receiving our power supply from, because this device is designed to operate at a 12-volt power as if it was in a vehicle. So we're using this battery to power it to represent that. So here we have our negative lead and our positive lead, and they run from that. Over here we have our ground pin, which is this one here. Both pins here are ground. This wire here coming off, and this wire or grounds going to the actual device. And as we can see, they go over here. And over here we will have our power here, which is going to connect to this bus bar, which powers the board, as well as we have a fused power input going to our board here and to our power supply unit. This board here, the actual circuit board itself, is an actual relay board out of a fire apparatus that uninstalled due to a breakdown on it that has an error over here in this area. But the rest of the board's fine, so I decided to use it for this project because it seemed applicable, as that this project is for stuff of this nature. So this board here is of an older style than what this is a representation of. This here would have to receive all of its inputs on these two connectors here. It received all of its inputs on these. There was a secondary board that plugged on top of it in this spot here. We can actually see one of the headers here. There's 4 headers around, and I'm actually utilizing this one here. And it would receive some of those inputs, process them, and output them appropriately onto all these relays. So as we can see, we have 14 relay outputs on this board, as well as about 10 or 12 of these just fused outputs. They're just solid power, they're not switched. And they all come off this bus bar. So instead of having to have all these wires, which as we can see, these are 20 pin plugs. So we have 40 wires coming just to the board, as well as we have 15 wires leaving this, 12 wires leaving over here, and including all these other inputs and outputs on the board for other options that were on this. So we have close to 100 wires coming to and from this single board, which is a lot of weight, a lot of time, and a lot of places for things to go wrong in an automotive setting. So what this design is for is to prevent all that. So what we'll be doing in this demonstration is I have four relay outputs here. And even though there's nothing connected to them, and as we can see, if I can get it zoomed in enough, we have these spade plugs here, which are for the output of the relay. But we also have this LED. So this LED signifies power output from this relay here. And it receives its power from this bus bar here through a fused input. So here we actually have a fuse, and I just put in random fuse power This one happens to be a 15. And all it does is if for some reason more power was pulled through this relay than we want it to, it would pop this fuse here, and so that we wouldn't have exceeding our power limit of the actual board itself. So these 4 relays are being controlled through this system here. Now this seems like a lot to control 4 relays, but there's more to it than just controlling them. So this here is where our inputs are going to be received. This is the slave or input device. And the reason I'm saying slave is because of the way this board communicates with this board is through an I2C protocol, or I2C protocol. There's multiple names for it. And it uses a master device and a slave device. The master device here, which I'm using this is a off-brand version, but it's a Arduino Mega platform. And this is an Arduino Micro platform. And what they're doing is they're talking to each other through these 3 wires here. This black one is a ground. Our white one here is where the actual data is being transferred. And the gray one is a clock sync, so that they know that they're on the same time scale for transferring data. Through that, they will transfer all the inputs to this board. So what we're doing is on this board, between our power wires here, this is our ground and our power coming to these rails. But this wire here is going to control this relay. So they counts down like this here. So we have the farthest relay, the second farthest, and then our third farthest. Or I'm sorry, our first and our second relay. This is our ground. These 2 here do something special. They control those relays in a special manner. Our white wire, if it is in a negative state, when the orange wire changes states, the relays stay in the same condition, and it controls these 2 here. This will be much easier to see here in a minute when it's actually visualized. When our white wire goes into a positive state, those relays will follow our orange wire, whether it's positive or lower. So we also have these 2 wires here going to this board. This is just to power this board in this demonstration, instead of having a separate power supply. So on this board here, we have our Arduino Mega board, and then we have a Altera Cyclone 2 FPGA. And what's happening here, if I'll remove our programming wire, I'll slide it out of the way, make things a little bit easier to see. This is our programmer here for this FPGA. So it is attached to the board, so that all you need is a USB cable to program the board. So in this setting, we have our input board. We have our Mega. This is where it receives the inputs to this board. This receives inputs at this board and transfers them to this one. So the way this is supposed to be is this can be in the whole other separate compartment of the vehicle. It could be another end of the vehicle, anywhere in the vehicle in which we want to have an input. And this is going to be where our outputs are outputting. And then, so it's going to receive our inputs here. And then it will, here, if we can see, we have 5 wires here connected to the output portion of this board. They follow right through here and come down into some of the pins of our FPGA. Now, if you notice, there's a lot of extra pins in between these boards. This represents that we can add this many more input outputs. So we can add multiple of these boards all through these same 3 wires. They're all connected together. So when it goes into this FPGA, the way this is designed is that the customer never has to program this board technically. They would dump the program on this board and leave it alone. This board here will actually is the one that the user will program. It uses a user-friendly software that you can actually visualize the circuit and program it to this board. So we can use digital electronics such as AND gates, OR gates, things of that nature, and even into a higher complexity. Or we can have them just straight as inputs. So it is up to the user to learn a little bit of the technology itself, but it is still easy for the user to learn and utilize. So here we have a yellow and orange wire coming over into our board. It is difficult to see with the shadow. Yeah, there we go. We have a ground and a VN. What that does is actually receives power to that board so that it can operate. And then we also have the same thing on this side here. This red and black wire actually go to the FPGA to power it. So here is where the actual circuitry is. We have this wire here coming from our FPGA's output over onto this board. So on this board, we have this here, which is a voltage regulator. What this does is it actually drops it from the 12 volt power being received from the vehicle battery and drops it down to a usable 5 volts for these boards here. So this side of our board is 5 volt power and this side is 12 volt power. So what we use here is we actually have a Darlington pair transistor, which I'll show now. So you can see it a little bit better. We have this transistor. And what it is it's a Darlington pair. And all it does is it's sort of similar to a relay, but in a solid state form. And what it does is it actually takes power through one of these pins, outputs power through one of the pins, and through one of the other pins, it will actually turn on and off those. It's mainly like an electronic switch. So what we're doing here is, we'll take this one for example. We have 12 volt ground. So these are using a negative polarity. So our ground wire here, it's still kind of hard to see, but it's actually going to our ground line, which is the blue side. So it will ground the relay. Then this wire here is the power coming into this transistor to be grounded. And it actually comes over into this header and it controls one of these relays here. So these relays have power to them right now from this bus bar to one side of our switch, which you can see in the diagram. It goes onto one side of the coil, and the grounded part of it actually comes through this. So we will ground the actual relay in order to switch it. So we switch our relay using this here. Here we have a resistor of 300 ohms, and it receives a little bit of power right here. So it's going to receive somewhere between 3 and 5 volts into here. It will go through this through this resistor and into the pin of the transistor here, this farthest pin. When that comes into it, it allows the gate inside the transistor to open. When that opens, it allows the power to flow through here and into the ground wire, switching the relay. So here we're going to power it up and actually see its transition work. Now it does have a power up state where some strange things occur, but that is just the power and stuff flowing through the device, powering it up. So now we're powered up and we've seen the strange clicks, and that is just due to the way in which this is being switched on. That could be corrected with furthermore delays and other things and of that nature being added to it with further research and development. But right now we see that this relay here is on. So as I was describing before, these two relays switch based off of 2 wires. These 2 relays have independent switching. So if I can get them in the same frame, I'll try my best. So this green wire here powers this relay. The blue wire powers this relay. Then we have our orange and white. So we'll see here if I can do it in the same frame. I'll switch it over to the power, and we get power on, back to ground, power off. So we're switching this based off of its state, and it's fairly fast. Same thing with our blue wire. So our orange and white wire, this is where things seem complicated, but is to show the versatility of the FPGA. So our white wire, as we can see, is grounded right now, as well as our orange. If I remove this orange wire and put it into the power, nothing occurs. Back to ground, nothing happens. If I move this white wire over to a high side on the power, as I move this orange wire, it switches relays. And we'll switch back. So it follows this between relays instead of just on off. Now I have no true honest purpose for this, but it is just utilize this to show the versatility of this system. So if I switch back to the low side, I can switch none. But if I'm in high and switch up, we already go up. So it will not switch that until the white wire is high. This is basically a very small version of this system, but this system has high potential and could be grown into a much larger and more developed system. It can receive analog inputs all the way to output analog or output pulse width modulation on a solid state relay or solid state output. For more information, please look at our technical report. It will have all this information in it and more. Thank you.